In progress.
All right, sorry. A minute or so. Oh, all right, so go ahead and get started. Well, I guess it's got like a minute or something, but I'll just start with some announcements as um, class period's about to begin. So the department has hired somebody to replace me for teaching this course. Um, her name is Kelly. Um, I'll be having a meeting with her tomorrow, just talking to her about some things. I've already kind of passed her information about the course and things like that. Um, from what I've gathered from her, she's going to make sure to not make many significant changes to how the course is going to be run and structured and things like that. I doubt she's going to really change the schedule from what it is. The major change that will occur is that she is not comfortable teaching in person currently, and so the course will be completely online. Now it will be synchronous, if you will, right? So she'll still have, like, say, this Zoom meeting. And, she'll have a new link as I'm the host of this, and so she'll set up a new link and things like that, right, and disseminate that to you guys. But there'll still be a regular Zoom meeting at 2 every Monday, Wednesday, right, for the rest of the semester. It's just that there won't be, the option of also attending this lecture live in person in Chem, what's this, 105 or something like that, right? So that's going to be the main difference. It's just that there isn't going to be a face-to-face option if for those who prefer that. But otherwise, I imagine that she won't change things significantly, and likely, uh, and so it's still being worked out as to whether or not she's starting next week or the week after that. Even if she starts next week, my guess is, I'm talking for tomorrow. I'm just going to be making this first exam anyways. And I'm giving her my old exams as well, so she can kind of see how I've done the exam, things like that. Maybe she'll decide to use them. Maybe she'll modify some for her own. I don't know. It depends on how much work she wants to, create for herself, basically. Um, but yeah. So uh, so I'll likely be making the exam for next week either way. The only thing is if the if I am still kind of the instructor for this course come next week, I'm still going to have to do the course online. So starting Monday, the course is going to be completely online no matter what, because I have to start my new position Monday. It's a remote working position, so but the point being is I won't be able to be here on campus. So yeah, so that's going to happen. So I'll let you know. The thing is, it depends. If she's taking over on Monday, then things might be a little different than if I'm in charge on Monday, and so I will have to just do. If I put an announcement on the Canvas page, people get that. I know I made like one or two announcements at the very beginning of the semester on there, and haven't done anything since that. Do people get that? Is that fine if I do it that way to disseminate information? Um, for the people in class and getting some head nods. If that's potentially not going to work for somebody, let me know. But I mean, otherwise, that's likely what I'll do is I know she's talking with Bill later today, and then I'm going to be talking with on Thursday. And so, by Friday, I'll know more about what exactly is happening next week. But for sure, you'll have your exam next week on Wednesday. But it might be, and so maybe this will kind of work out for the best. But I think what will likely occur is just, well, I'll have plans for Monday next week for myself, and maybe she'll just do the same thing. Is we'll just take time next week on Monday on kind of reviewing things that we talked about for thermal chemistry and some of the kinetics we talked about today. So it'll be more of kind of review. But yeah, and so the main the thing is I my I don't know if I'll be available at say 2 o'clock for Monday, so it might be a situation where if I'm in charge of the class, I'll try to set up a time that will fit and work for my schedule to do things live, but otherwise just upload some extra videos of example problems and things like that for Monday in preparation for your exam on Wednesday. And so how the exam will work, since the class will be online, right? Oh, leave current meeting to join a new one. All right, I'm going to decline Bill's invite to talk with me. Um, yeah, sorry about that. I don't know if Bill meant to send me a meeting invite. But anyways, so how the exam will work is basically, so I guess I haven't thought about some of this, but essentially it'll be posted on Canvas. You'll answer questions and things like that, and then upload your work onto Canvas. You'll have to, yeah, yeah. So I'll send out more information. I shouldn't have started talking about exactly how the exam will work, besides just that it's going to be given on Canvas. I'm debating, with students at this level, right? You guys have already gotten your bachelor's degree and things like that. I'm not as concerned about all of you cheating, right? This sort of thing. So it might be, when I taught this class last time, I think for maybe it was the final exam, I ended up just kind of giving it to people and let them take home and work on it and eventually give it back to me. And so I might do at least this first exam and, see kind of what Kelly has planned, or maybe I'll talk to her how she would like to do her exams, just trying to make it consistent. But could be that, either the exam is uploaded and you can just over like an 8-hour time window, grab it, take it, turn it in or whatever. Or it might be something where it's like available during class time and you just got to, be available during class time to take the exam and submit it by the end of the class period type of a thing. So I don't know if it'll be that timed or not. I'll have to kind of look into that, think about it, and as well as talk to the new person about how she plans on doing the exams in the future as well. But yeah, but it will be available on Canvas and posted there. So yeah, again, I apologize about this change as the semester is going. I know it's not easy on you guys, and myself and Kelly, I'm sure will appreciate your ability to kind of adapt and flow with the situation as is. But yeah. So any questions people have kind of about the course, about things. And again, if you ask me questions and I don't know the answer, in terms of like, what is the new professor going to do? It's not a bad thing to ask me those questions just to make sure I didn't have those questions in mind to ask her to then be able to disseminate that information to you guys, type of thing. So I don't know if there are any questions that people might have, again, about just kind of the course, the structure, and what's happening in the future with someone else taking it over.
So should we go ahead and complete the homework
Yeah. Yeah. So the only thing is you have to submit it online, the homework, instead of submitting it in person. So I will. I don't think I set that up yet. So I'll after class sometime today, I'll set up a like homework one thing for online submission. So you can just upload a file on Canvas and submit it that way. We do the same time, by end of class period on Monday type of thing. So we do by 3:20 on Monday for that first homework. Okay. So yeah, so that will still be due. And after it's due, I'll post the answers as well online, so you can always check kind of your work compared to the answers. If you have questions, email me about those and things like that. Okay. But yeah, so the homework is still going to be due next week. And other questions? Here, I don't see. Yeah, so all right. So let's get going on kinetics then. All right. So just as a review, right? Chemical kinetics, right, is a study of rates of reactions, right? It's going to tell us obviously information about speeds of reactions and things like that. But kind of the more important thing that we can learn from kinetic studies that's used all the time in all aspects of chemistry is understanding the mechanism of a chemical reaction, right? So we use chemical kinetics to be able to understand at the molecular level how a reaction is occurring, right? And through that information, we can then use our knowledge of chemistry to try to manipulate the reaction, right? Maybe we want to speed it up, maybe we want to slow it down, maybe we want to cause some other reaction to occur than the one that is happening, right? And so we say, well, maybe if I do this modification here, add an electron withdrawing group here, put on a bulky side group there, right? And modify how these reactions are going, right? If we understand the reaction mechanisms, then we're able to do those type of things, right? And so it's very important to kind of understand that stuff. And so being able to measure in lab rate laws and the dependence on the rate of reaction based off the concentrations of reactants and such, and then relating that with the rate laws predicted for mechanisms is a very common thing, right, that we often do in order to try to make sure that we understand how a reaction is occurring. Okay, right? Because all the time you'll see in plenty of chemistry papers proposed mechanisms, and typically you need to justify why you think this is the mechanism, right? You do some NMR studies, maybe you try to isolate an intermediate, right? Maybe you do some Kinetic studies of changing hydrogen to deuteriums, if there's some hydrogen transfer involved or things like that, you think, you know, can look at that, or even just changing, atoms from hydrogen to deuterium to kind of see where the deuterium ends up in the final products and things like that, right? And trying to maybe probe using IR, NMR, these chemical reactions as time's going on to study the change in certain peaks and stuff, right? All these different things we use to try to verify whatever we think the mechanism is for a chemical reaction, right? That's all related with studying the kinetics and how a reaction occurs, right? Thermodynamics that we've been talking about is all caring about what is our reactants and what are our products, right? What will happen spontaneously, right? What direction will the reaction want to go given these conditions and things like that, right? Kinetics is all about how does that reaction occur, right? And so that's what we're going to be talking plenty about in the study of kinetics. Okay, right? And so when we talk about kinetics, we talk about rates of reactions. Okay, now given some reaction here, I could talk about, say, the rate of consumption of some reactant, rate of formation of a product. Okay, okay, and those rates can be different, especially based on these stoichiometric coefficients, right? If I talk about the rate of consumption of B versus the rate of formation of C, right? Well, C, I form 3 of them as this reaction is going, right? So the rate of formation of C should be 3 times faster than the rate of consumption of B, right? Just based off of our balanced stoichiometric coefficient, right? So if I define the rate of the reaction as just, say, the rate of formation of C, and someone else decides to define the rate of the reaction as the rate of formation of B, we'll get different rates of reaction, right? And that's not good. Every reaction has a rate it precedes at, right? And so we want to define sort of a reaction rate that's independent of what we measure, right? Whether or not I'm looking at the concentration of B, C, A, or D in this reaction, right? I want to report the same rate of the reaction. And so we define the rate of the reaction as kind of these ratios, right? It's the rate of change of our reactants and products divided by their stoichiometric coefficients. So when you divide those rate of change by their stoichiometric coefficients, you'll get the same rates for everything. And so that will give me, so then if I measure the rate of change of C and the rate of change of B, right, I will get the same number for the rate of the reaction using this definition, right? So all of these things at the bottom of the slide here equal the rate of our overall chemical reaction, right? And that's just kind of by definition of what the rate of the reaction is. Questions about that? Again, hopefully a lot of this stuff that we start off with will at least be review. That's a lot of things that we get to. Right, and so, right, we care about, for these rate of reactions, we care about how the rate of reaction depends on temperature and other factors, including concentration of our reactants and products, right? And the dependence of the rate on concentrations is given by our rate law equations. And our rate law equations have the general kind of form given here of some rate constant times concentration of reactants or potentially products, right? The rate constant kind of lumps in the temperature dependence and other things into the rate. And then otherwise, you have then the explicit dependence on concentration in your rate law, right? The units of that rate constant, right, as mentioned at the bottom here, right, is varying depending on what the rate law expression is. Okay, so K, the rate constants don't have just a unit, but the rate of the reaction has a unit. It's molarity per second, right? The rate of reaction is molarities per time, concentration per time, right? Concentrations have a unit, it's molarities, right? And so the units of Kr is just whatever it needs to be for the units on your rate law to work out. So in this example, Kr will have units of 1 over molarity, 1 over second. Because if you take 1 over molarity, 1 over seconds times molarity, you'll get molarity per second, which is the units of the rate. Okay. So yeah, so the rate constant itself, its units will depend on the rate law expression, right? But again, the rate law is giving us explicitly how does the rate of the reaction depend on concentration. So questions about this? All right. So just note that the rate law doesn't have to be simple. Okay, right? For this, and we may do this example later, to kind of see, and not necessarily today, but this simple looking chemical reaction H2 plus Br2 forming 2HBr. Okay, it has a much more complicated rate law of Ka, which is some rate constant times H2 times Br2 to the 3/2 over Br2 plus Kb times HBr, right? And obviously here, HBr is a reactant in this, or is the product in the reaction, right? So it obviously depends on, you know, what, the product here. And again, these concentrations of reactants and products both can appear in the rate law, but as we'll talk about when we talk about mechanisms, right, intermediates aren't going to appear there, but products can. Products can affect your rate law, and that's fine. Right. And so, right, again, if we're thinking about units of these rate constants, okay, right, thinking of what the units are is just going to depend on what do they need to be to make the units in this equation, in this rate law work, right? And so, right, we want to think about what those units are, and I'll flip over the slide real quick in just 1 second, or not the slide, but flip to the what I'm writing down. Right. So, if I'm writing out kind of units for this rate law, right, the rate itself, the molarity per second, right, and then I just plugged in molarity for wherever I saw concentration, right? So in the denominator here, right, I have molarity plus something times molarity. So units of Kb has to be what? So this one's a little trickier. Kb itself actually has no units, right? It's unitless, right? Okay. Now, how this actually ends up working is Kb in the actual mechanism is like a ratio of some rate constants and things like that. So that's how it ends up being kind of unitless. But in general, right, Kb has to be unitless here because, right, concentration plus concentration, if Kb has any type of units, that math doesn't work, right? To add two numbers together, they have to have the same units, right? I can't add Fahrenheit with Celsius, right? I can't add joules with electrons, right? I have to add up things in the same unit, right? I don't add joules with kilojoules. And so, right, so Kb is unitless, okay? And then the other term here is right, and then so now the question is Ka, right? Well, for Ka and my denominator, I have units of molarity, right? And so, right, so one of those units of molarity will cancel with the units of molarity on the top half, right? So we're gonna I have kind of molarity over seconds is with Ka. I'll just put molarity 3/2, and then roughly molarity on the denominator, right? And so just simplifying things down, right? Moving the 3/2 over here, right? You'll get that Ka has units of 1 over molarity 1/2 seconds. Right. Again, so it has this kind of weird fractional unit and so on, right? And yeah. So questions about this? Oh, would the molarities be different reactants? M's. Oh, so the M's in that in my expressions there were shorthand for like molarity, right? Moles per liter. So the different M's were just all moles per liter. So I was writing out, you know, sorry, I was writing out this rate law here in terms of writing out just what are the units for everything in that rate law, right? I was writing the units of V, units of H2, concentration of H2, units of concentration of Br2, so on and so forth, right? So I was just writing, so M is molarity, it's moles per liter, and that's, yeah, so I was just writing out the molarity, the units for that, just to figure out what are the units for Ka and Kb, not like numerical values or things like that, but just what are the right, and again, hopefully some of this stuff's a reminder, right, in terms of orders of reactions, right? The overall order of your reaction is just a sum of kind of the exponents in your rate law, right? The order with respect to a specific reactant is whatever its exponent is in the rate law, right? So this reaction is order X with respect to A, order Y with respect to B, and X plus Y. You know, for the overall order of the reaction. Okay? Right, so if I say a reaction is second order, that means the exponents in the rate law all add up to 2, right? And if there's say only one reactant, then the rate law is that reactant's concentration squared, right? Because it's second order, right? Or if I say a reaction's first order with respect to B, second order with respect to A, the rate law is Kr A squared B, right? So right, the order is just giving you the exponents that appear in the rate law expression. So there's different ways we can get to these the rate laws experimentally. There's I should have had something here, right? There's one thing called the isolation method. That I don't have that written here on the slide, okay? But the isolation method is just sort of this idea. Let me change the share screen here. Isolation method, right? Is the idea, let's say, again, I have some reaction that has A plus B going to C, right? That's my reaction, right? So I'd say my rate law is some Kr, some concentration of A to X, concentration of B to Y. Okay. The isolation method, how that works is basically say, let's, put in a lot of B, right? So let's just say we have a large concentration of B and a very small concentration of A, right? So the concentration of B, right, is much greater than the concentration of A, okay? Well, as the reaction's going, right, that concentration of B, if it's much greater than that of A, as the reaction's going, right, even though its concentration is changing, it's not changing significantly, right? The idea is, let's say I have, 10 moles of A and 1 millimole, or sorry, 10 moles of B and 1 millimole of A, right? Well, when I react up all my 1 millimole of A, right, my 10 moles of B is still basically 10 moles of B, right? I've used up just such a small fraction of B that its concentration is effectively constant, right? And so the idea is I have an excess amount of something, so its concentration, right, is constant, right? So we basically say this as a constant value, right? Constant concentration, right? And so what that means, right, for my rate law is that I'm going to call K prime R concentration A X, where K prime R is just KR concentration B to the Y, right? It's since B is constant, I'm just going to lump that in with the rate constant and just look at it like this, right? And so now why this is called the isolation method is right is now I've isolated the concentration dependence of my rate law for just A, right? Now I'm just focusing on how the concentration of A affects the rate of the reaction, because the concentration of B is basically constant, so I can think of it as, effectively just within the rate constant itself and isn't appearing in the rate law, right? So this is kind of the isolation method. And so this is done, quite often, right, in order to solve for rate laws, right? Because if the concentrations A and B are varying during this reaction and things like that, it can be difficult to tease out the dependence on A and B at the same time, right? But it's a lot easier to keep one constant, have one sort of as a control, if you will, right? Keep it constant and vary only the other. Okay? So again, that's what the kind of isolation method is all about. Right? And so with that, you can do something like, say, the initial rates, where once you start the reaction, you know what the concentrations are, right? Hopefully you measured out the concentrations in the lab before you start your reaction. So you know what those concentrations are, so you can measure that rate initially. And then what you do is you just vary the initial concentration. You just do multiple reactions at all different initial concentrations, measure that initial rate, okay? And then you can make a plot, for example, of that initial rate versus the rate or the concentrations, right? Those initial concentrations, and the slope of that plot is going to give you the power of the exponent for that reactant, right? It's going to tell you the order of your reaction with respect to that specific reactant. Okay. Right. Now, the only thing is this method of initial rates, right, isn't going to be able to predict, say, this rate law here, right? Because you have no products initially, so this is just zero, right? And so the rate law that you get from the method of initial rates for this reaction is going to be different from the actual rate law, right? And so to test that, right, you have to do some things to study what is the rate, how does the rate of the reaction depend on BR2 as time goes on, right? And so yeah, so this method of initial rates, if products appear in your actual rate law, it's not going to show up, right? It's only going to be able to test reactants because you have no products initially, right? The idea. Okay. Right, but again, that's the idea of the method of initial rates is you just measure these initial rates for different concentrations since you can control what the initial concentrations are, right? If you're not able to study what the concentration is of something as a function of time through some sort of spectroscopic measurement or something like that, right? Then you can use this to get out the dependence on that reactant, okay? But if you can just measure the concentration as a function of time, right, then you can do some other techniques that we'll talk about, right, with getting the order with respect to that reaction. Okay? But I mean, effectively, what you would do is you, instead of doing the initial rate, you just measure the rate over time, measure the concentration over time, and make the same type of plot, right? You could get the slope that way. Questions about the method of initial rates? All right. So, right, in Gen Chem, you saw this, and who knows if you've seen it since then, right? But got a question in chat real quick. Why do we need it? Can you repeat? Why do we need it? Why do we? Oh, so you might need to do this, say, method of initial rates if you're not able to measure what the concentration is accurately of your reactants as your reaction's going, right? So, let's say, there's not really a unique IR peak that you can study while the reaction's going, or an NMR peak or something, right? That you just can't really do some sort of measurement to know what is the concentration of your reactants as the reaction's going, right? Then in that case, you can use this method of initial rates because you can at least control what the initial concentration is. So if you can get the initial rate and you control the initial concentration, then you can just change the initial concentration and measure the initial rates and make a plot of that to get what the order is with respect to a reactant. Okay? So that's why you might need to use this method in the lab, is if you can't measure those concentrations as a function of time. Does that kind of answer your question? All right. Right. And so the so this type of question here is, yeah. So what you would do is you would measure the rate as the reaction starts, right? You measure what your concentration is at the start of the reaction, right? Before you start the reaction, right? You have reactant A and B, right? I measure out what are their concentrations before I mix them together and let the reaction to start, right? And then you measure the rate as the reaction starts, right? Because as the reaction is starting, the concentration of your reactants is that initial concentration, right? And so then you know what the concentration is because you measured it out before you started the reaction. And then you measure the rate in some way, right? And then from that, you can get what this rate law expression is, right? What is the order of the reaction with respect to a specific reactant? But yeah, you do need to measure the rate as the reaction is going. So before the reaction, you get the initial concentrations, and then you start the reaction and measure that rate as the reaction starts, and then you don't worry about it, right? And if you're using this method of initial rates, once you get that initial rate, once you get the rate of the reaction, once it's starting, then you don't really care what happens after that, right? You're just caring about what happens initially. And so, how you might record the data is something like this, right? You have, three different experiments you ran, right? You did one experiment where you had some initial concentration of A as 1 times 10 minus 3, B is 1 molar, and then that initial rate you measure in lab to be 2.5 times 10 minus 3, right? And you do this same experiment with different initial concentrations as shown here, right? And then what we can do is, using this data, is we can determine what the rate law is for this reaction, okay? Because let's see, maybe I've just typed out. Let me see here. Oh, well, something happened with formatting. But right, but the idea is, right, the general rate law should look something like this. Like it should be something like this. Maybe it ends up being more complicated, but it should be something like this, right? That for my reaction, A plus B going to C, right? That the rate law should look something like this, right? The question is what is X and what is Y, right? Well, if I run two different experiments, so I measure the rates of V1 and V2 are the rates for experiment 1 and experiment 2, right? So experiment 2, experiment 1, right? Well, the rate for experiment 2 will have some rate constant, and then it will be the concentration of A for experiment 2 to the X power, concentration of B for experiment 2 to the Y power, right? And then again, experiment 1, right, is K times concentration of A for experiment 1 to the X power, and concentration of B for experiment 1 to the Y power, right? And so you do these two experiments, right? And then if you were to do the ratio like I show here, if, for example, if you keep the concentration of A constant, so A2 equals A1, right? The concentration of A in experiment 1 equals the concentration of A in experiment 2, okay? Then they will cancel in this expression. These are equal to each other, so they just cancel with each other, right? They go away. And so if this is true, let's say A1 is equal to A2, right? Then you'd have this ratio B2, B1 equals, and then the rate constants cancel, B2 over B1 to the y power. Oh, sorry. It's not on there all the way, right? So you then have the ratio of the initial rates versus the ratio of those concentrations, right? And you'd have this equation where then it's easy to then solve for what that power is. What does y need to be? Okay. And so that is what we do here, right? So for example, if I do trial 1 and trial 3, right? So experiment 1, experiment 3, right? If I take the ratio of the rate laws for those experiments, right? The concentrations of A will cancel with each other because they're both just 1 times 10 to the minus 3, right? Concentration of B increases by a factor of 2.5, right? And then here, this looks like it will increase. What are they going to be? 2.5 squared. I mean, so how I do this mathematically is, well, yeah. So this ratio, so the ratio is set up right here on the slide, right? You know, annotate here, right? So this is what we're doing for B, right? So for B, right, for trials 1 and 3, concentration of A was the same, so that stuff just cancels out, okay? And then I have a ratio of 2.5 to 1 raised to the y power, and 1.6 times 10 to the minus 2 divided by 2.5 times 10 to the minus 3, right? Well, this is basically this ratio of 1.6 times 10 to the minus 2 divided by 2.5 times 10 to the minus 3 is 6.4, right? 2.5 divided by 1 is 2.5. And so in this equation, if you solve for y, right, you'll get that y is basically equal to 2. Okay. And so yeah, so and then you do the same thing for trials 1 and 2. Again, I apologize, the formatting got messed up here. But trials 1 and 2, as you see the data, right, the concentrations of B are the same. Okay. Right. And so since those concentrations of B are the same, right, they will cancel out in this expression and it doesn't matter. Okay. And so you're just left with 2.5 divided by 1. So 2.5 to the x equals 2.5, right? So x has got to equal 1. And so your final rate law is then just, I shouldn't have the not here, just the final rate law itself is V equals KR times concentration of A times concentration of B squared. Okay. So questions about this example here? Oh, apparently I need to clear off the annotation that sticks around. I'll draw this out. And if you want to find the rate constant, all you need to do is take the data from any one of your 3 trials, right? In lab, you would take the data from any one of these 3 experiments, plug in that data, and solve for the rate, right? So plug in for what the rate is measured, what the concentrations were, and just solve for the rate constant. Okay? Get something like this here, 2.5 inverse molar squared inverse. Questions on this example? All right. So that's kind of, again, just our introduction to kind of what is our rate law, how might one try to experimentally determine them in the lab, okay? Right, and just kind of intro to kinetics. We'll talk a little bit about some integrated rate laws, focus on kind of first and second order reactions. And then after that, we'll jump into mechanisms and spend lots of time on mechanisms. Talk about chemical kinetics and mechanisms for polymerization reactions, for photochemistry, for enzyme kinetics, and other such things. Okay, so we'll spend lots of time just going over mechanisms and talking about different mechanisms and how you solve for the rate laws of these mechanisms and what kind of tells you about them and so on and so forth. Okay. So, all right. So if we have some first order reaction, okay, it'll have a rate law of the rate equals Kr times concentration of A. Okay. Well, again, that rate of the reaction is related with the rate of change of the concentration of A, which is your reactant, divided by time. So again, this is first order with respect to some reactant A here. So A is assumed to be a reactant. Okay. And so plugging these two things, kind of setting them equal to each other, okay, there's two equations for the rate of the reaction, okay, you get this differential equation, dA dt equals minus KRA, which has a simple solution when you integrate it to give you, the concentration of A equals the initial concentration times E minus KRT, or the natural log of A is minus KR plus the natural log of A naught is kind of familiar form, right, for that. Okay. And these are referred to, these equations on the bottom of the slide here are referred to as the integrated rate laws, right? Because they're called integrated rate laws because you literally get these equations by integrating the rate law, right? So, I mean, not a very clever name to call them the integrated rate laws. It's literally all it is integrating the rate law expression to get these equations. Okay? So the first order integrated rate law has this expression. Again, the natural log form here, you maybe have seen it before with the natural log of A equals minus KT plus the natural log of A naught. Here, I just combined the natural logs using the fact that the natural log of x over y is equal to the natural log of x minus the natural log of y. Okay. So I can show kind of how you can manipulate that natural log expression if you want to get maybe the form you've seen more familiar, more often. But yeah. So no, you will not have to integrate rate laws or things like that. The only integration that might appear on an exam will be when you get to like quantum mechanics, because quantum mechanics and not even really spectroscopy. It's all it'd be just kind of like intro to quantum mechanics stuff. All that stuff has a lot more kind of integration involved, and I don't like. I'm trying to remember if I think maybe there's like one question on one exam with intro to quantum mechanics that had some integration on it, but otherwise, so kinetics, thermodynamics, no, there's going to be no integration needed for these things. It's going to be basically algebra stuff. And when you talk about spectroscopy and other things like that, again, there won't be any kind of integration derivatives. So only very briefly within the course might you need to worry about doing anything like integrating. And typically for those, you would probably just be given like integral table, and have to look up what the integral comes out to be. All right. Right. And so if I have that integrated rate law, right, given here, right, if I measure the concentration as a function of time, right, and what would I want to plot, right, in order to get a straight line for my expression, or for my concentration over time? What am I plotting? Am I plotting concentration versus time? I'm plotting the exponential, the logarithm, the inverse of the concentration. What am I plotting versus time to get a straight line given the integrated rate laws here? What would you say? Right, but I wanted to make sure this was a first order reaction. What would I plot? So we want to plot the natural log of the concentration versus time, right? because that will give you a straight line, right? This is like y equals mx, right? Plus b, where b is the y-intercept, which happens to be 0 if you plot the natural log of a over a naught, right? But you plot the natural log of that concentration, the slope of that line. If it's a first order reaction, it will be a straight line, and that slope will give you the rate constant itself. Okay. And again, so this is another way you can try to figure out what is the rate of your reaction, right? Is plot the concentration versus time, or say the natural log of the concentration versus time, things like that, and see, right, how that varies, right? See which gives you a straight line. Because if it's first order, only plotting the natural log of the concentration versus time will give you a straight line, right? If it's second order, it will only be 1 over the concentration versus time will give you a straight line. And in 0th order, it would be concentration versus time will give you a straight line, right? So there's one unique way to get a straight line from these plots. And we still teach this stuff in chemistry and things like that, because this is how people did stuff initially, because it's very easy to figure out, is a line straight, right? If I ask you, figure out if this is a natural log function or 1 over x or something like that, right? That's not so easy to just eyeball, to just look at it and say, oh, that looks like 1 over x, or that looks like the natural log, that looks like x cubed or something, like it's very difficult to figure those things out by just looking at it, right? But I can tell you if a line is straight, you know what I mean? And so often, right, in science, we try to fit things to straight lines, right? It's easy to get the slope, it's easy to interpret, it's easy to do lots of things with it if the data can be represented in a straight line in some way. Okay. Right? And the other thing we care about with these integrated rate laws are half-lives. Okay, the definition of the half-life is just the time it takes for your concentration to reduce by 1/2 its initial value, right? That's why it's called half-life, right? How long does it take to get to half its initial concentration, right? So for a first order reaction, right, that's the concentration is 1/2 the initial. Plug that in here, right? And you'd simplify, and you'll get that, the time it takes is that T1/2. And so when you simplify that equation, you just get the half-life is equal to the natural log of 2 divided by the rate constant. Okay? And the half-life is always inversely proportional to the rate constant. Okay? No matter what the order of your reaction is, right? The half-life is always inversely proportional to the rate constant. Okay, right? The larger your rate constant, the faster the reaction, the shorter the half-life is going to be, right? Because you're just consuming your reactants at a much faster rate. Okay? But only for first order reactions is the half-life independent of concentration, right? Notice that the initial concentration never appears here in this final expression, right? So whatever that initial concentration is doesn't matter, okay? Which is very, very convenient. Okay? This is why we can do things like carbon dating without having to like completely, consume an entire fossil, right? Is I can take a small sample of my fossil, and from that sample figure out what percentage change has occurred, and use that without knowing what the total concentration is. Okay, right, and so right, and I might even have an example of carbon dating at some point, right? But yeah, okay, but so we get that half-life, okay, right, by just kind of solving this equation, and yeah, this formula is true for first order reactions. It's not true for second order reactions. Will depend on the concentration. 0th order reactions will depend on the concentration. This is only true for first order. There's a different half-life expression, if you want to call it that, for each order of the reaction. Okay. So this is only true for first order reactions. Just keep that in mind. Okay. All right, yeah, this is just iterating what I talked about, right? For radioactive decays and things like that, those are first order reactions. Their half-lives are independent of concentrations, right? So you can just say that half-life for this first order reaction is this, right? I can't tell you what the half-life is for second order reaction because the half-life depends on the concentration. So it depends on how much you have, right? But only for first order reactions is the half-life something that's independent of concentration, so it's unique to that reaction, okay? Right? The half-life is unique to the reaction and does not depend on what you have or how much you have, right? Okay. All right, so any questions? Oh yeah, this is an interesting example. Let's see what get this. Yeah, let's do this. So here's something that we'll look at a situation where you have two parallel first order reactions. This is going to pop up later in kinetics as well and things like that. This is a common thing that can occur, especially in spectroscopy and photochemistry and things of that nature, having two parallel competing first order reactions. But here, right, I have this acetic acid that can decay to two different sets of products. Okay. Now the acetic acid at high enough temperature will decay to both products at given the rate constants provided here, 5 inverse seconds and 8 inverse seconds, right? And the question is what is the maximum percentage yield of the ketene product, which is that CH2CO, right, at this temperature? Okay. And we'll see that the answer to this will be very simple once we get there. Okay. Grab a new sheet of paper here. All right. Okay, so we're interested in what is the maximum percent yield, right? What is the maximum kind of theoretical percent yield, right, of CH2CO, right? And so how would you in lab determine the percent yield of a product from a reaction? Say that again? Yeah, right. You'd weigh out how much of the product you have, and what would you do with, and how much reactant you have, right? And right, so you just write the percent yield, right? So that percent yield CH2CO, right, is just what is the final, right, concentration of CH2CO, right? What is that final concentration over the initial concentration of CH3COOH, right? Right, what is that initial concentration? You know, and if you want a percentage, right, you multiply it by 100, right? But right, that the percent yield is just asking what is the final concentration of CH2CO, right, versus the initial concentration of CH3COOH, right? And so here we can actually solve for what is kind of the maximum theoretical yield for this reaction, right? Where I have two competing first order reactions. Okay? Right? And to get that, what I need to find out is I need to find what is this concentration of CH2CO, right? What is that final concentration if I let this reaction go to completion? Okay. Well, I know, right, that the rate of, you know, that the rate law for this reaction here, right? So the rate for that second reaction, reaction 2, right, is just K2 times concentration of CH3COOH. I'm told it's first order reaction with respect to CH3COOH, right? So that's the rate law, right? And again, I know that because, I mean, it's not shown here, but again, in the problem, it says these are first order reactions, right? So it's first order, meaning it's got an exponent of 1, right? So that's rate law, right? Well, the rate of the reaction, right, is just related to the rate of formation of CH2CO, right? I mean, they're just directly equal to each other, right? So the change in concentration of CH3CO or CH2CO over time is just equal to K2 times CH3COH, right? I don't know what the concentration of CH3COOH is as a function of time off the top of my head, right? But I know, right, the rate of change for the concentration of CH3COOH over time, right? I know what that is. Well, that's related, right? The CH3COOH is going to lose concentration based off of how fast the first reaction goes, right? Right? So the rate of that first reaction. And then it's also going to lose some concentration based off the rate of the second reaction, right? Well, the rate law for the first reaction is just K1 CH3COOH. And the rate law for the second reaction is just K2 CH3COOH. Okay. And so this simplifies down to just negative K1 plus K2 times concentration CH3COOH. Okay. DCH3COOH dt. Okay. Oh, sorry, that's dropping off. Okay. So I have this equation here that relates how the concentration of CH3COOH changes with respect to time. Okay. And note here that this is just a first order rate equation. So it has just an integrated rate law. Concentration of CH3COOH, right, is equal to the initial concentration of CH3COOH times exponential of the rate constant times time. Well, here the rate constant is this K1 plus K2, right? This is effectively KR, right? My rate constant. So this is K1 plus K2 times time. Okay. And so this, right, is how my concentration of my reactant changes over time. Okay. We're not quite done yet, but I'll pause here, right? See questions about why I'm doing what I'm doing, how I got what I got, and so on. Any questions so far? Pause just a second here to see. Could you explain how you got V1, negative V1 minus 2? Yeah. So basically, right, so kind of zooming up here, okay, right, how did I get this equation right here? DCH3COH dt equals minus V1 dt, right? So, right, if I want to know how does the concentration of my reactant CH3COH change with time, right? Well, I lose, right, the speed in which I lose my concentration is related with the speed in which my reactions are going, right? If this first reaction goes at 1 molar per second, the second reaction goes at 2 molars per second, right? The overall change in my concentration is going to be related with that 1 molar per second added with that 2 molar per second, right, together. Now there's a minus sign here because the concentration decreases with time, right? So it's a negative, okay? Right, these rates of our reactions are always defined as a positive value, okay, right? Like if I want to do this in more detail, what I could say is, right, if you recall, right, for this first reaction, right, the rate of the reaction, V1, is, equal to K1 CH3COOH because we're told it's first order, right? But by definition, the rate of the reaction, V1, has to equal minus dCH3COOH dt. It also has to equal dCH4 dt, and it also has to equal, right, dCO2 dt, right? That rate of the reaction, by definition, is related with these rates of changes, right? They all have a stoichiometric coefficient of 1, so that's why there's just a factor of 1 in front of all those things, right? And so, right, and so I see how there's this negative, right? If I multiply by the minus sign here, right? That's how I get this is related with negative V1, and then I can do the same thing with here V2, right, to get it equal to minus V2, right? And so that's where, right, this equation here comes from, right? This dCH3COOH dt equaling minus V1 V2, right? This is the rate of reaction 1, right? And then this is the rate of reaction 2, right? And it's just right how fast those rates are, right, determines how quickly I lose my reactant, right? Faster the reaction, the faster I lose my reactant. Okay, and they're just directly equal to each other with a minus sign because the stoichiometric coefficients in these equations are just equal to 1. All right, right. And so now I have this equation here that tells me how the concentration of CH3OH depends on time. And I can just plug that back in to this equation up here, right? Okay, so that I can get dCH2CO dt equals K2CH3COOH, initial concentration, and e to the minus K1 plus K2. Okay. So I get this equation here, okay, which then this is a differential equation that you can integrate and solve for, okay. And when you do that, you basically get either 100 space here, right? Again, you don't need to worry about how to integrate this, how to do some of this stuff, right? How to do this next step. Again, I'm doing it in class because I want to kind of get to the punchline of this because it's a very useful kind of punchline in general, and we'll be able to apply it to any type of kind of system. We'll talk about in a second, right? But when you integrate this out, you'll get that the concentration of CH2CO as a function of time is just K2 CH3COOH dot the initial concentration times divided by K1 plus K2 times 1 minus 1 minus 1 plus here. 1 plus. Is plus? No, shoot. Hold on. No, it's got to be minus. Yeah, it's got to be minus. Minus E minus K1 plus K2 times time. That. That's fine. Yeah, and this minus gets okay. Yep. So this is what it comes out to be again. Don't worry about how I got there. If you don't know math, that's fine. The main thing is like what we're concerned about. Okay, right. Going back to the initial question, right? That percent yield of CH2CO, right, is related with the final concentration of CH2CO, right? So the final concentration is we let this reaction go to completion, right? We wait as long as needed for everything to react, right? So we wait an infinite amount of time, right? So this equation here, right? So the final concentration, right? The final concentration of CH2CO, right, is when time goes to infinity, right? You wait an infinitely long amount of time, okay? And so when you do that, you get that this final concentration of CH2CO is equal to K2 CH3COOH naught over K1 plus K2. Okay. So you get this for the final concentration. Okay. And so if you plug that back in to this initial expression here, you see that this initial concentration of CH3COOH goes away when you plug in for that percent yield. Okay. Let me just get out of blank pages. Oh, I can flip it over in the back here, right? So what you'll get, plugging this in, right, the percent yield of CH2CO will end up being K2 over K1 plus K2. Okay, it's literally the ratio, K2 over the sum of the two rate constants. Okay, because again, this initial concentration dependence will cancel, right? Because your original percent yield, right, is the final concentration divided by the initial concentration. Okay, right, and so yeah, your percent yield is K2 divided by K1 plus K2. I think all of this is also, oh, no, I didn't work it out on the slide. Okay, never mind. I didn't work it out on the slide, so never mind. It's not worked out on the slide, but let me go back to this solution here. So and one of the key things about this and why I wanted this example, okay, is this very simple thing, right? In terms of rate constants. And so this type of thing, right, the percent yield of some product, right, when I have competing first order reactions. So I have these parallel first order reactions, right, is always going to be the rate constant of that specific product you care about over the sum of all the rate constants, right? I'll say sum over I, right, of all the different rate constants, right? So this is important to say in photochemistry, if you're talking about percent yields of your singlet excited state or a triplet state, you're looking at fluorescence or phosphorescence type stuff, or your percent yields, for things. If you have these competing first order reactions, there's this general expression that pops up over and over again, that it's the rate constant of the thing you care about over the sum of all possible reactions rate constants, basically. Okay. And so again, this thing pops up a lot in photochemistry, but it can appear in other aspects of chemistry, and other mechanisms and things like that. If you have, again, competing reactions for some sort of reactant, okay, if there's some type of first order reaction, you'll have this type of thing, right? Nuclear chemistry also has this pop up, because some atoms, some molecules, or not molecules, but some atoms have different nuclear decay products, right? And so if you want to know what is the percent yield for some nuclear decay product, it just depends on what is that rate constant for those different decay products, right? But yeah, so this general, not general question, but this specific question of, I have two competing parallel first order reactions, right? Doesn't really matter what those reactions are, right? As long as they're first order reactions, right? So parallel just means that they are independent of each other, right? That it's not like CH3COOH forms this stuff and then CH4 forms the product that we want, right? It's not linearly dependent, right? It's not one after the other. They aren't sequential or things like that, right? They're happening at the same time, competing with each other over the same reactant, right? Then you get that just the percent yield of whatever you care about is just going to be related to those rate constant ratios, right? And so, right. So if I want to get a certain product, right, then I obviously need to increase the rate of that specific reaction compared to the other one, right? Which conceptually makes a lot of sense, right? but you can also see that kind of pop out in the math if you have the ratio of those rate constants. Okay? So questions about this example, again, the steps you took to get to the final answer are not something that you're going to need to be able to reproduce or redo. Okay, so don't worry too much about being able to redo what I kind of did and kind of skimmed through and jumped over and kind of the derivation of the final answer. Okay, I just wanted to arrive at that final answer to kind of talk about its significance and the fact that it pops up in different aspects of chemistry. Will you get a formula sheet on the exam? That is a good question. Yeah, I mean, probably. I haven't thought about that. I think that's what I did last time. But yeah, so likely so. Again, I will be talking with the person who's taking over for the class tomorrow and talking about kind of how she's thinking doing things, how I've kind of done things, and what I would be planning on. And you know, I will make sure that whatever I'm doing, she'll be doing, whatever she'll be doing, I'm going to be doing, things like that. So there's not a difference between exams, difference between homework, things like that, right? Want to try to keep this semester as consistent as possible, despite having two different people teaching it. Okay. All right. Yeah, we got a few minutes. So going to second order and things like that, it's right. The same derivation of the second order integrated latent law, right? You write out this differential equation, you integrate it out. Again, you don't need to worry about doing it. You get this equation here, right? 1 over the concentration is equal to the rate constant times time plus 1 over the initial concentration, right? Which is an equation for a straight line, right? So you plot, 1 over the concentration versus time. And if you get a straight line, then that's a second order reaction, right? And the half-life for second order reaction, right? Again, you plug in the definition of the half-life into your integrated rate law, simplify, you get the half-life here again, as I was mentioning, right? Does depend on the initial concentration. It's inversely dependent, right? So the larger your initial concentration, the shorter your half-life, right? And so, if your nuclear decay was a second order process, right? You would need to know what is that total initial concentration to know the half-life, to be able to know, right, how long your sample has been there. Okay. In which case, again, you'd have to destroy an entire fossil or something like that, right? Or I guess you could estimate, assume it's a homogeneous mixture and blah blah blah. Take large enough sample, right? But because these things are first order, right? Nuclear decays. That makes things like carbon dating and a lot of other things like that a lot easier and kind of simpler to do because it doesn't depend on the initial concentration. Right? Okay. So questions about the second order, right? Integrated rate laws. It's just like the first, it's just a different form, right, of that. But again, if ever you're wondering, right, what is the concentration of my species at some period of time, that type of question, right, what is the concentration at some time, or how long does it take to get to a certain concentration, right? Those type of questions always need to use integrated rate, right? If you're ever trying to relate concentration and time in some way, that's an integrated rate law type problem, right? You're going to need to use your integrated rate law, right? So that's always a key that I tell people to hone in on, right? If you see concentration versus time type question, right? That's an integrated rate law type question. Okay? All right. Right. The temperature dependence of reactions. Might be able to get through all of this. Yeah. Temperature dependence of a reaction is given by the Arrhenius equation, right? The temperature dependence of a reaction, right, is through the rate constant. The rate constant, right, has this Arrhenius equation form, right? The equation itself, was originally determined kind of experimentally, found empirically, right, and later kind of form of this equation was derived using kind of Boltzmann statistics and transition state theory. But the Arrhenius equation here is this form where the rate constant equals some pre-exponential factor A, the Arrhenius constant, or frequency factor, times exponential minus the activation energy is what this EA is called, right? Divided by RT. Okay, right? The activation energy, right, is a like energy barrier, right, that is required to go from reactant to pump. Okay, so that's what that activation energy is, right? How much energy you need to overcome the lowest possible barrier that gets you from reactant to product. Okay, right? Based on the Arrhenius equation, right? The larger your activation energy, the stronger temperature dependence you have, right? The activation energy is very small or non-existent. You'll have no temperature dependence for your rate. Okay, and then the units of this pre-exponential factor is just the same as the rate constant, which just depends on the rate law itself. Okay, there's no net unit for A. And typically you don't really talk about what is the value of A and stuff like that. That's not something we'll focus on. We'll mainly focus on activation energy, right? Because it's often stuff we care about with kinetics and mechanisms, right? What is the activation barrier for some reaction, right? What is that transition state? How can we maybe modify things to lower the activation barrier of that reaction and lower the energy of that transition state? Okay. If you want to look at the temperature dependence of K, you can, if you were to measure the rate constant at two different temperatures, okay, you could just take the difference between the rate constants of those two temperatures and end up with this formula here, right? Natural log of the rate constants at two different temperatures is just the activation energy over R times the difference of the inverse of those two temperatures. Okay. All right. Yeah, we haven't talked. All right, I think based off time, we'll kind of end it there. The last type of stuff that kind of talked about is kind of ideas of transition state theory, which is basically the idea for a reaction to occur, your reactants have to collide in the right orientation, and they have to have enough energy to overcome that barrier, right? Well, the energy to overcome the barrier is given by like a Boltzmann distribution. We won't worry about that. Okay, but using that is kind of how you get this Arrhenius form. Okay, from Boltzmann statistics and kind of this transition state theory, right? And the other temperature dependence, again, I'm just kind of talking about this now, but we'll talk about it later on Monday next week. But the last thing we'll talk about temperature dependence is just kind of, this thing we often think about in chemistry, right? Thermodynamic versus kinetic products and kind of how we can relate things and what's going on, right? Okay. And why is there such a thing as a thermodynamic and versus kinetic product and times, and what does that mean, right? And that will finish up kind of the kind of that aspect of kinetics, and then the rest of kinetics will all be on reaction mechanisms. Okay? So I won't. Yeah, like I said, we'll see on Monday in terms of if I'm in charge of the class or if the new professor will be in charge of the class on Monday. If I'm in charge of the class, I don't plan on starting kinetics or reaction mechanisms. I'll kind of tell her that, so she'll probably kind of do the same thing. So I think Monday will be kind of more just kind of finish up these last few parts about kind of, again, discussing temperature dependence of your rate constants and things like that. And then just kind of reviewing some example problems and things of that nature, going over questions. People have questions about kind of the homework that's due on Monday, can go over that or potentially things like that. So in kind of preparation for the exam that's going to be on Wednesday. Okay? But yeah, otherwise that's it for today. And yeah, I will potentially see you next week. Again, starting next week, there will no longer be any in-person version of this class. It will be all strictly online. But again, there will be it will be synchronously online, I think is what that's called, right? Where there will still be meetings at regular class time, things like that, right? There just won't be someone in the room at Chem 105. I guess if you want to come to the room and plug in a laptop and project Zoom on, the screen or something like that, I guess you could, because I don't think there'll be anyone else in this room, but I don't know why you'd necessarily want to do that. All right, so see you guys later. And I guess if I don't see you later, the best of luck to all of you, in your master's degree here and things like that. And if you ever have questions, related to things with exam one, questions throughout the semester, I mean, you can still email me. I'm happy to try to answer questions, help how I can, right? I'll still be around and things like that. Not necessarily on campus, but I'll be around the area in Texas and things. So yeah.
Last time, but for the syllabus,